So we'll be doing calculation topics first. Okay, so we'll so it's not in the right order in the syllabus, but energetics involves calculation. So since we are doing moles, or we were doing moles, so this will be done before the rest of the topics. Okay, specifically atomic structure and chemical bonding. We're going to leave that till later on. I said now energetics. That's related to energy from chemicals in O levels. As an energy, that's what's the unit for energy? That's usually it's kilojoules. It can be joules as well, but most of the time in chemistry, the term that's used is kilojoules. I mean, joules and kilojoules are the same thing. There's no difference, but the unit that's normally used is kilojoules. You've got exothermic. Okay, what does that mean? That means energy is released. Or produced. And you've got endothermic. That means energy is absorbed or gained. When some reaction is exothermic, there's going to be a rise in temperature. Heat is going to be produced. And when something is endothermic, there's going to be a drop in temperature. Because heat from the surrounding is going to be absorbed. And remember, whenever you measure the temperature, you're measuring the temperature of the surrounding, which means that if something is absorbing energy, there's going to be less energy in the surrounding. So you got exothermic, endothermic, you already know all of this. The sign for exo का sign होता है. What's exo and what's endo? Which one is plus, which one is minus?
Plus is endo.
ठीक है, plus is positive is endo and negative is exo. And also remember that when you talk about energy, plus 100 and minus 100, like on the number line, if plus 100 kilojoules and there's minus 100 kilojoules. Now, remember on the number line, plus 100 is a bigger number, but when you talk about energy, plus and minus are the direction of the energy. They're not, they don't represent the quantity of the energy. Both of them are exactly the same amount of energy. Number line, it's obviously plus 100, that's bigger than minus 100, but when you talk about energy, it's the same exact energy, right? No one is greater, no one is small. It's just the direction of energy. Is that clear?
Yes, sir.
So don't confuse plus and minus with greater or lesser. It's the same quantity. So then you've got now related to chemical reactions. Let's talk about exothermic reactions. Do you have any examples of exothermic reactions? Okay, which reactions do you know of are exothermic reactions? Any reaction? Number one, which one is exothermic? Anyone?
Combustion.
Combustion is one, that's exothermic. So we've got combustion. You've got neutralization, acid-base reactions. They're all exothermic. So some energies you should know of. Combustion is always exothermic. Neutralization is always exothermic. What else is exothermic? Changes of state. If you go from gas to water, liquid to solid, right? In that case, there's going to be there's going to be a loss of energy. And that's number 4. You've got nuclear reactions. that produce a lot of energy. Number 5, what's number 5? That's you've got yeah, there's other exothermic reactions. Respiration is exothermic. Okay, that's how your body produces energy. Anyways, etc. So you must know some reactions, their signs. And then similarly, you've got endothermic reactions. So any idea which reactions are in endothermic?
Thermal decomposition.
Okay, so number 1 is yes, thermal. So number 1 is thermal decomposition.
Then electrolysis.
So you've got electrolysis, second. I said what's the opposite? What's the opposite of electrolysis? That's a photochemical cell. That's exothermic that produces photochemical or galvanic cell, or just a cell, simple cell. Okay, that's exothermic. I say electrolysis number 3. What's what else? You can have
solid to liquid gas.
Because solid to and then gas. You can also have photosynthesis. That's you can have photosynthesis. That's some examples of common endothermic reactions. So you've got exothermic reactions, you've got endothermic reactions. Which reactions do you think can happen at a fast or more feasible or can happen easily? Exothermic or endothermic?
Exothermic.
Okay, so they tend to be more feasible. Not always, because there's activation energy as well, but obviously they don't need energy, so they don't need energy from outside, so they're more feasible. While endothermic reactions, they constantly need energy, so they're more feasible. No energy as such needed, overall needed. Except the activation energy, which is EA. Endothermic reactions, they constantly need energy. The moment you stop providing them energy, they'll stop happening. So they're more feasible. Endothermic reactions would be more feasible at higher temperatures. Now, if I want to boil water, water is not going to boil at a lower temperature, right? It's not going to be feasible. But if you increase the temperature, it's going to become more feasible at, like if I want to boil water at 1000 degrees centigrade, that's definitely going to happen. So they're going to be more feasible at higher temperatures. Why? Since they need energy. ऐसे ही हो गया. बाकी है कि since they constantly need energy. I say now in every reaction, every reaction has 2 steps. And the first step is, like if I do a reaction, example, there's hydrogen reacting with Cl2, and together they're going to produce HCl. Now, first thing is, hydrogen is bonded with the other hydrogen atom. So the 2 hydrogen atoms are bonded together, and the 2 Cls are also they're also bonded with each other. So the two Cls are also bonded with each other, and when they react, they'll produce an HCl molecule. And they're going to produce two HCl molecules. So that's one. And here's the other one. I said, so how does the reaction happen? The reaction happens because this molecule is buzzing around, it's roaming around, and it's going to collide with this H2 molecule. That's also, so there's some energy that is required. The molecules need to move around. They have to be energetic. And when they're energetic, they're going to bump into each other and they're going to collide with each other. And one thing will happen, which is that bonds are going to break. So all bonds are going to break. And that would lead to the creation of, so when there's a collision, and you have to give them a lot of kinetic energy. That's why you heat things up. Like if you want to burn wood, why do you have to heat it first? The reason is, okay, there's, if there is wood, and there's oxygen molecule, this is a piece of wood and there's oxygen molecules around it. Why don't they start burning? They don't start burning because the oxygen molecules are not moving around with a lot of energy. So the oxygen bonds do not break. When you provide it with heat, the oxygen molecules, they now travel faster. They've got a lot more kinetic energy. So when they go and hit the wood or the molecules in the wood, the old bonds are going to break and the new bonds are going to form. So the first step involved is always you have to provide it with some activation energy so that the old bonds can break. And then when the hydrogen and Cl atoms have broken apart, so all the hydrogen atoms and the Cl atoms are now flying around and they're totally broken apart into pieces. Now they're going to randomly combine with each other and they're going to form HCl molecule, and that's new bonds are going to be formed. Is that clear?
Yes, sir.
Which part is endothermic? Which part is exothermic?
So bond breaking is endo.
Because the first part, bond breaking, is endothermic. That's that always requires energy, and the next part, bond formation, it's exo. All the work, the reason it's exo is all the work is going to be done by the atoms themselves. Like if you've got a hydrogen atom that's flying around with 1 electron, and you've got a Cl atom that's flying around with 7 electrons in its outer shell. Now the Cl nucleus, there's a positive nucleus in the center, right? Let me remove the Cl. Both atoms have a positive nucleus in the center. The Cl nucleus will try to attract the electrons from the hydrogen atom towards itself. So it's going to do all the work itself. No energy is needed from outside. So the hydrogen atom is going to get pulled and it's going to gain kinetic energy. And where is all that kinetic energy coming from? It's the Cl that's pulling it. So all the energy is coming from Cl. Cl pulls that electron, and that's why the hydrogen atom, it gains kinetic energy. So energy is produced in this way, and energy is always movement. It's always at the molecular level, at the atomic level, it's produced in the form of kinetic energy. The particles, they travel a lot faster, and that's how heat is produced. Is that clear?
Yes.
So in bond formation, all the work is done by the atom itself. It's interested in electrons, so it starts pulling on those electrons. Anyway, so now the next part is, and that leads to the first formula, which is, if I were to calculate the enthalpy change for this reaction, the enthalpy change is the net energy change for this reaction. So the first formula is going to be that it's the energy that's it's going to have a positive sign. So it's the energy that is consumed during bond breaking, or that is needed for bond breaking, and minus, because it's exothermic, it's the energy that is released during bond formation. Right, so that's going to be our first formula. Is that clear? Sadi clear? Ahmed, Rafi clear?
Yes.
Yes.
So remember, there's just 4 or 5 formulas that you're going to study. This is the first one of them. I'm going to make an energy profile diagram as well, which you've also done in IGCSE. So the energy profile so the energy profile diagram is K so you're going to have 2 diagrams. One is that products, and then you've got reactants. So that's a first one, products and reactants. Products and products and reactants. So initially at the start, energy is gained. Why? Because you're breaking bonds. And then at the end, energy is released. Why? Because you're forming bonds. So now is this one exothermic or endothermic? Econ, which one is this?
Exo.
Yeah, that's exo, because more energy is being released. The initial amount of energy that is needed to start the reaction, that's your activation energy, because you need to break bonds first. So that's EA, activation energy. What's the definition of activation energy? It's simply what it is. It's the energy that is needed to start a reaction. To start a reaction. And then enthalpy change. Remember, I made one mistake, which is that I labeled them incorrectly. This one is I said then we've got enthalpy change, which is you start off at reactants and all the way to, that's the net energy change. So that's your overall delta H. And in this case, this one is for an exothermic so this one is for an exothermic reaction. Okay. Is this clear? This one? Clear?
Yes.
As Baki, we can have the other one, which is endothermic. Let's do that quickly. 1 second. So endothermic में क्या होता है? That's reactants have less energy compared to the products. This is how it kind of looks like, and so here are my reactants, and here are my products, and the activation energy, again, all arrows are going to start from the bottom. That's your activation energy. That's the energy that is needed to start a reaction, and that's my. So in this case, you need a lot more energy in an endothermic reaction. You need a lot more energy to break bonds. So bonds break, and over here bonds formed. So now less energy is given off when you're forming bonds. So this one is endothermic. So this one is endothermic. Now we've got exothermic reactions, we've got endothermic reactions, we've got activation energy. You don't need to go further into this, right? You already know all of this, right? Clear, Sara?
सर एंडोथर्मिक में एंथैल्पी का साइन कितने?
Endothermic में क्या होगा? अच्छा, delta H.
एंथैल्पी साइन.
Delta H is this one, right?
ओके सर.
अच्छा, delta H is this one. But remember, all arrows must start from reactants. Okay, that's over here. This is the amount of energy that is needed to start the reaction. That's your activation energy. Over here, this is the amount of energy. So the activation energy is smaller. So that's the energy that is needed to start the reaction. Or delta H overall. That's reactant to product. Reactant to product. That's delta H. How do you reduce activation energy? I say activation energy. If it's greater, is it going to be a fast reaction or a slow reaction? If you have, so if the energy that is needed to, इसी को थोड़ा सा discuss करना कि it's, so activation energy, it's large EA means slow reaction, because the reaction will probably not happen or will happen at a very slow rate because a lot of energy would be needed to start the reaction. So that's one thing, like rusting of iron. You've got iron, you've got oxygen in the air, but very slow reaction. Because it would probably be very hard to break the bonds of iron. So next is how do you reduce activation energy? Okay, EA can be reduced by what?
Time taken to start the reaction.
How can you reduce activation energy?
Or reduce catalyst.
EA can be reduced by adding a catalyst. So you can EA can be reduced by adding a catalyst. Now, what will happen to this graph if I add a catalyst, the graph would become lower in height. So it would instead be instead it will be traveling a smaller distance. So that's the same graph.
Sir? So what is the difference between the average bond energies and activation energy?
The energy needed to break the bond? इसकी बात कर रहे हो?
Yes, sir. So the average bond energy or activation energy same.
It depends. Not exactly, because it can be the same thing. Okay. But I'll explain later. Okay, we haven't defined what bond energy is yet. Okay, so they're not really going to be the same thing. Okay, when you do a reaction, right? So you're not just breaking the bonds. You're doing other things as well. Like if I want water to react with something, so I would need to break the ONH bonds, right? So that's bond energy. You clear enough? If I want water to react, I would have to break the water bonds. Is that clear?
Yes.
But I would also have to break a lot of other forces as well. Okay, the water molecules are वो सारे आपस में जुड़े हुए. They're all attracting each other. So I would have to first separate the water molecules from each other. Okay, that's known as an intermolecular force. So imagine if I want water to react, right? And there's liquid water. So the first problem is that the water molecules are very strongly, I mean, that's why they're in liquid state, because the water molecules are strongly attracted to each other, right? So I would have to break the intermolecular force. And then I would also have to break the bonds as well. So when I want to start a reaction, I would have to do a lot more than just breaking the bonds. Okay. Firstly, we've started energetics. Okay, this is a topic. So we just started it. So hopefully we're just doing energy profile diagram. So you'll probably you've already studied this in O levels as well. थोड़ा सा advanced पढ़ेंगे भी, but we're just doing basics at the moment. So I hope you'll catch up with this. So you clear, Faraz? Is this clear? Hello. कैसे पूछा था? Rafi, sorry. Faraz के लिए. Rafi, is this clear?
Yes. Yes.
So the point is that starting a reaction requires a lot more than just breaking bonds. It's breaking the attractive forces that are even if the water is sticking to a glass, you would have to sort of make the water molecules separate from the glass as well. So a lot more energy is required to start a reaction than just breaking bonds. So when I write bond breaking, it means all sorts of things. It's intermolecular forces, but we'll come back to bond energy, the one that you're talking about. Anyways, moving to this. Remember activation energy, what does it do? It if it's very high, it slows the reaction, and it can be reduced by adding a catalyst. So activation energy can be reduced by adding a catalyst. Now, coming back to the same question, why did you have activation energy? The reason you had activation energy was that the old bonds had to be broken. Hydrogen cannot react with Cl2 unless you get rid of the H bond and the Cl bond, and the atoms are free to move around, and then they can sort of recombine and form something else. To break the bond, you would have to give them energy, and to give them energy so that they collide with each other. So how does a catalyst reduce activation energy? It does that by many different ways. Okay, one way is that I'm going to talk a bit about catalysts because now there are two types of catalysts. There's a thing called homogeneous catalyst. Now, a homogeneous catalyst means that it has the same state. So it has the same state as the reactant, or it's in the same phase as the reactant. That's a homogeneous catalyst. You've got plenty of examples for homogeneous catalyst. One of them is we can thought esterification is one. If you remember esterification from everything was aqueous, right? And the catalyst was acid. So you had an acid catalyst, H2SO4. So they were all in aqueous state. They were all in the same physical state. So that's one example. And there's another type of catalyst, which is a heterogeneous catalyst. So heterogeneous catalyst is that it's got a different state than the reactants. So the point is, how does a catalyst reduce activation energy? How does it make it easier to break bonds? Anyways, this one is a different state. What examples for that? Haber process. In Haber process, everything was a gas, and the catalyst was iron, which is a solid. So it had a different state. So that was the example in this case. So moving on, how does a catalyst reduce activation energy? Just give me 1 second. So opposite, but how does a catalyst reduce? Now every reaction has a certain problem. Like for example, if there's this reaction, which is done between it's a reaction that happens with S2A2 minus plus I2. Just a second. No, it's between plus 2I minus 1, and this is what happens, that a reaction happens. So a reaction happens and you got 2SO4 2 minus, plus we've got I2. So you've got this reaction. Now the whole question is, how does the catalyst work? Now, if you look at this reaction, why do you think this reaction has a very high activation? Every reaction has a different reason why it has high activation energy. Now, these two are trying to react. No, you've never studied this reaction, so ignore the reaction. Just look at, just think, use your common sense. Why would it be so hard for this reaction to happen? This one is S2A with a charge of 2 minus. This one is 2 iodized ions with a charge of -1. So just use common sense. Why would it be very hard for these two? Huh?
Same charges.
Same charges, right? So the problem is that this reaction is not going to happen because they have the same charges and the same charged particles are going to repel. So the trouble will be, like, one of the particle has a -2 charge, the other one has a charge of -1. Imagine them swimming around in the solution. You want them to react together. Now, for them to react together, they would have to interact with each other. They would have to meet each other, but they're not willing to meet each other. They would be repelling each other. So it would be really hard for them to actually even come close to each other. There's going to be too much repulsion. So large amounts of energy would be required. The only way you can have this reaction, you can make this reaction happen, is that one of them has both of them have high energy. They've got high kinetic energy. Okay, that's the only way they would be able to overcome the force of repulsion. That's the only possible way, and they'll be able to collide. So that's why a large amount of energy is needed. So every reaction has a different reason why it needs high energy. Is this clear? This one, why this reaction is not happening, right? Is this clear?
Yes, sir. Yes, sir.
Yes.
So now to reduce activation energy, there are a number of ways of doing that. So every reaction has a different reason, right? So if I want to reduce activation energy, now in this case, an alternate path is provided because the reaction is impossible to happen in this way. So what they do is they provide an alternate path. So what is done is Fe3 plus ions are added as catalysts. What they do is they create two paths. I mean, these two are not going to react with each other. That's the given. These two will not be produced. Too high in activation energy. Impossible for the ions to meet or interact with each other. So an alternate path is given. So you add Fe3 plus as a catalyst. What that Fe3 plus does is that it goes to 2i minus 1. Now 2i minus 1 is not going to react with S2i2 minus because of the negative charge. But instead it does get attracted to Fe3 plus. Why does it get attracted to Fe3 plus? Because it's obvious that it's got a positive charge, right? So it goes to Fe3 plus, gives electrons to Fe3 plus. Fe3 plus becomes Fe2 plus. And iodine is formed. Then that Fe2 plus that is formed, it goes to S2O2 minus, where S2O2 minus gains electrons from it, and 2 Fe3 plus is again formed, and 2 SO4 2 minus is formed. So what's happening here is that, so this is just an example. You don't have to, I'm just trying to explain how the activation energy is reduced by adding a catalyst. These two were not going to react with each other. So we wanted them to produce these two things, but they were not willing to react with each other. So when I added Fe3 plus, which had a positive charge, the negative ions were automatically attracted to the Fe3 plus. I minus 1 gave electron to it. It became Fe2 plus. I2 was formed. The Fe2 plus was S2A2 minus was wanting to lose electrons. It gave it to Fe2 plus, and this is formed. Forget what's happening. Just think of the alternate path. Is the alternate path easier to happen? The negative ion attracted to a positive ion, right? So it's got a much lower activation energy. Is that clear? Ye baat clear?
Yes.
Yes.
And are the two things forming? Iodine is getting formed, and SO4. I mean, your both products are getting formed, right? So both of the products are getting formed, but they're formed in two steps now. What happens to the catalyst? It remains unchanged. You started off with Fe3 plus, you ended up again with Fe3 plus. So the catalyst that you had added is still there, and you got both of your products. So the point is, you don't have to remember all of this, right? It's just in A2 you would have to remember this. You just have to remember homogeneous catalyst, which is and you need to know how, or just some brief idea of how a catalyst functions. I'll give an example of heterogeneous catalyst as well. You don't have to remember the equations. They might give you the equations and they might ask you, how is the Fe3 plus acting as a catalyst here? It remains unchanged and it lowers the activation energy. The two ions were negatively charged and it created an alternate path, and which reduces activation energy because now they are oppositely charged ions. Okay, so the equations, don't remember them. If there is a question, they'll give you the equations, but just the functioning of how a catalyst might function. Okay, is this clear, this example?
Yes. Yes.
Yes.
Okay, so that's one way, alternate path. Create another totally different path, right? And then we'll talk about heterogeneous. We'll talk about it in the next class then. Okay, how can a catalyst? What are other ways of a catalyst working to reduce activation energy? So we'll pick kal karte hain, theek hai? Abhi bas basics, just basic stuff. We just did basic stuff. All of the stuff did this formula, we didn't do bond energy as such. We just did what happens in a typical reaction. Bonds are broken, bonds are formed. You got energy profile diagrams. There's activation energy, that is energy that's needed to start the reaction. I also told you that's not exactly, it's not exactly the energy. It's not, we didn't do bond energy. TK Rafa, don't confuse it with bond energy. TK. When I refer to the term bond breaking, that could mean a lot of things. TK. Then TK, let's continue tomorrow then.
Okay. Allah Hafiz.
Yeah, Allah Hafiz.
Love.